Okay, in the last video, we talked about how to write vectors. Now I'm going to, and I showed you a bunch of numbers, but I didn't tell you where they came from. Let's try and go into that by talking how you convert from polar to Cartesian. All right, so, and then obviously the next video, I'll show you how to go from Cartesian to polar. And as needed, I'll try and talk about 3D vectors at some point. All right. So a lot of times in the real world, we're talking about things moving around. Maybe it's a plane flying or a person walking. We usually have north, south, east, and west. Unless otherwise specified, we usually pretend this is the x-axis, east, and this is the y-axis. This is just kind of our normal default. Okay. And our goal is to get to Cartesian form. If you remember, the Cartesian form is some vector that looks like Vx in the I hat plus Vy in the J hat. So we need to figure out Vx and Vy. Step one, if it's a 2D vector, you can draw it. Okay, this will help. So now just kind of eyeballing this thing. I got a protractor here for me. Just kind of eyeballing it. Let's see, so this is about 30, about 37. So I'll just kind of keep that there. Isn't perfect, but generally speaking, if you can try and draw your arrows and angles approximately to scale, it will help a lot. Most important, try to avoid drawing everything like a 45 degree. This one's kind of close to that, but hopefully you can tell this side's bigger than that one. That makes a difference. So we're told it's 36.87 degrees west of south. Start at south and go west by 37 degrees here. So I'm going to start at south and go this way. 36.87 degrees. Am I on the right whiteboard? I am. Okay. So here we go. And in this case, I know the size of it, the magnitude is 5.00 meters per second. The magnitude is this. Here is the angle. The trick is to think of this like a triangle. I forget which one I used last time. I think I had purple was going down. And then this one's going over. Somebody else out there might be saying, whoa, why don't you go over and then down? Either one works. In practice, I call this Vy, but the minus sign is included right here. We see this is going downward, so we expect a negative number here. More on that in a minute. This is also Vy, just like this is Vx. We'd otherwise expect a negative number because it's going to the left. Here it is. So at this point, I might redraw this as just a simple triangle here. You could leave off the units as long as you remember to put them on at the end. So I'm going to draw this as a triangle here, and I'm going to choose to put the arrowheads on. You might be saying, how do you know whether it goes up, right, left, or down? Remember, this arrow is going down and to the left. That's why I chose these arrowheads the way I did. One of them's down, one's to the left. All right. So in this case, I'm going to call this angle theta, so it's easier to draw. So just so you know, this angle right here, I'm calling theta, because it's easier to fit in the picture than third. And I recommend you do that in your homework, right? You don't want to fit all these tiny little angles and write really small. Okay. So in this case, I'm using SOHCAHTOA. You probably know that sine of an angle is equal to opposite. Well, this side we're calling Vx, and this side we're calling Vy. We're ignoring the minus signs for the minute, but we'll put them back in at the end when we look at the arrowheads. That's just in practice what I do. You can do whatever you want. This works for me. Again, I just forget the minus signs, but then remember to check the arrowheads at the final answer. So in this case, it's a triangle. Opposite of this angle is Vx. Hypotenuse is the 5.00. I see in this case, I'm just going to write it like this. Now I'm going to plug in what theta is. And when you punch that all in, hopefully you get, what was it, 3? Let's do it. So 5 times, whoa, oh, come on. 5 sine of, what was it, 36.87? I got 3. Now I'm actually going to include an extra digit here. Think. This number is only good to 3. This number is good to 4. I'm going to include 3 just in case I need this later, but I'm going to underline the digit where I might have a mistake. So in practice, this is kind of a handy way to show, look, I'm keeping an extra digit. That way, if I need to use this in subsequent calculations, I'm not rounding too soon. Okay. Now, from experience, you're gradually going to get to just jump right to this line. So in this case, you're going to be saying, look, Vx is opposite. Opposite is going to involve so I'm going to use the sine function. And instead of doing all this, generally speaking, I skip right to this step. That said, let's go ahead and do ca here. If I do ca, adjacent over hypotenuse would be, and then just to humor me, remember this is the magnitude V, right? So if I want to make I don't like writing all these symbols all the time. So instead of writing 5 meters per second, I'm just going to put V and not plug in the numbers until the very end. So now I see that Vy is V cosine of theta. And what I was saying before is usually you kind of jump right to this. You might be feeling a little bit uncomfortable right now. You might be saying, dude, the x component is supposed to get cosine. My math teacher told me that. That is true if the angle goes to the x-axis. But look at this angle. This is not the same angle that you got in your math class, is it? So that's why the x is getting a sine function and a y component is getting a cosine. Anytime the angles are drawn to the vertical axis, you'll see x gets a sine function in it and y gets a cosine. Anytime the angles are drawn to the x-axis, maybe this one or that one, then the x will get a cosine and the y will get a sine like you're used to. But this is correct, okay? All right, and you can tell by looking at it. Here's the advantage of drawing a good picture. We can tell at this angle, the x component had better be smaller than the y component. Why? Because I'm closer to the y-axis than I am to the x-axis. So it's got to be this way. When I punch in these numbers, let's see what I get. 5 cosine 36.87. And now you can see that I get I'm going to keep an extra digit. Yep. I'm going to underline where I should round. Think, what did I forget? Units. There's units on this number. There should have been units on this number. So there's units on this number. Always important to check the units. Okay. This is how you go from polar to Cartesian. And notice I didn't do a 3D vector here. Usually if you're doing 3D vectors, we just go straight to Cartesian in this class. So if I'm doing anything in 3D, I'm going to start in Cartesian and probably just work the whole thing in Cartesian. I could try to explain more to you. If you want to talk one-on-one, we can do that in office hours. So what have we done here? We converted a polar form vector into Cartesian. Ooh, we should probably write it and make sure we get the minus signs right. Remember, I was belaboring this point, like, oh, don't forget at the end, you got to think about this minus sign from the arrowhead and this minus sign. Oh, no, really, this should be a negative here. And this should be a negative because these are both going to the left and down. So when I write this all, that's how I got this vector in the last video lecture. The x was negative 3.000 I hat, I'll stick the units at the end, minus 4.000, there's the rounding digit, j hat. And then all of this at units of meters per second. That's usually how we write these. Now what we have done is we have converted this polar form vector into this Cartesian vector. That was the goal of this video. We're done.